Welcome again. By the name Senyo Simon, I'm going to take you through gas turbine engines. Yeah, I'm going to take you through some module 1 to 4. Yeah, this is module 15 by Easa. Yeah, let's start. First, I'm going to talk about the 4 stages of the Brighton cycle. Turbine engine uses the Brighton cycle. So this is how I came to divide the 4 stages in the Brighton cycle. First, we are going to talk about the intake stage. So here air enters and is compressed by the compressor. That is in the intake stage. And this intake stage, there's that cone that directs air through the engine. Next, we go to the compression stage. So in the compression stage, pressure and temperature increases significantly. This is when because we know that in the compressor there are multiple stages, so as air keeps on moving in these stages, its pressure and temperature keeps on increasing. Next, we are going to talk about the combustion. So in the combustion stage, this air will enter the combustor, then fuels are burnt and they expand in the combustion chamber. Now these hot gases will proceed to the exhaustion, which is the exhaust stage. Gases expand through the turbine and nozzle to create thrust. So next, here I talked about 2 types of engines. I talked about the turbofan engines and the turbojets. So I had to compare these two. The turbofan, they are the most commonly used commercial engines. Due to their advantages, they have a high bypass ratio, they have a better fuel efficiency, and they have a noise reduction. So this is the diagram of the turbofan engines. We have the front fan, we have the bypass, then we have the core of the engine. So from there, I talked about the turbojets. These turbojets were used in older design. They used for high speed, so high speed aircrafts, and all the air passes through the core. So all the air has to pass through this core. So design requirements, all these engines have a high thrust to weight ratio. That means they are compact but producing high thrust. Then fuel economy, low specific fuel consumption, and a gas turbine should have a long operational life with minimal maintenance. So now I proceeded to the engine performance or thrust and efficiency. So thrust fundamentals, we have the thrust equation here. You know that thrust is equal to is proportional to the mass flow rate, which is m subscript times the velocity change divided by gravity. Yeah, so here there's an example. You can calculate it and the answer you will get is indicated here. So performance efficiency metrics, we are going to consider thermal efficiency and propulsive efficiency. Thermal efficiency, we are converting fuel energy to heat. Then propulsive, we are converting heat energy to thrust. Next, we are going to talk about the environmental sensitivity. How does temperature affect performance of the engine, pressure variations, humidity impact, aircraft speed influence, and altitude dependency? Yeah. So here we are going to talk about the engine ratings and engine pressure ratio, which is the EPR. When you talk about the engine ratings definition, flat ratings maintains constant maximum thrust up to a specific temperature. So this engine should maintain a constant maximum thrust to a specific altitude and temperature. Then after limit, thrust decreases with altitude increase. As the altitude increases, the thrust will keep on decreasing. The engine, we have takeoff, maximum continuous, we have the cruise, we have the ideal. Then we talk about each rating has its limits for RPM, for exhaust gas temperature, and exhaust pressure ratio. So when we talk about exhaust pressure ratio, we are going to talk about the ratio of the turbine exhaust pressure to the compressor inlet pressure. Primary thrust indicator, so it is used as a primary thrust indicator, direct measure of the engine power output and used for engine thrust setting on the flight deck. So here we are seeing PT2 and PT7. If you divide the turbine exhaust pressure by the compressor inlet pressure, you get what we call the engine pressure rating. Now, performance degradation and environmental factors. When you talk about from recovery definition, it is the pressure raised in the inlet due to the aircraft forward motion contributes to the overall engine performance. So this ram recovery increases with the airspeed which is approaching the engine. Now, efficiency degradation, we shall talk about compressor blade, surface erosion. This one reduces efficiency. Foreign objects impacts, they affect performance of the engine. Turbine degradation due from high temperature. So regular maintenance to maintain performance. Yeah, we have to do regular maintenance, visual inspections, walk-arounds around the engine. Then we are going to talk about the altitude effects. As altitude increases, air density decreases. So what happens? Direct reduction in the engine thrust output. So it's a critical performance factor for aircraft operations, that altitude. Then when you talk about temperature effects, high ambient temperature reduces air density. So it leads to degradation of engine performance. Combined effect with altitude is significant. Okay. Next, we are going to talk about the inlet function and design principles. Yeah. So primary function, inlet duct as a diffuser. That's one of its primary function. Slows the incoming air velocity, increases static pressure, prepares air for compressor entry. It also minimizes turbulence and pressure loss. Ensures uniform high pressure airflow. Well, yeah. Now we are going to talk about the design types of the inlet ducts. We have the divided entrance used on older aircraft designs. Routes air around cockpit area, accommodates fuselage geometry as the divided entrance. Then the variable geometry used on supersonic aircraft manages shock waves at high speeds, maintains efficient air delivery, adjustable inlet geometry. Then the design objectives is to minimize energy loss, achieve maximum operation efficiency, provide distortion-free airflow, maintain compressor inlet condition. Now we are going to talk about inlet used as an ice protection and foreign object defense. First, we are going to talk about ice protection. Hot air from the compressor routes through inlet slip routes through guide vanes prevents ice accumulation, critical for flight safety. Here we are going to talk about anti-ice protection system. Yeah, these are the heated guide vanes, then hot air flow. Then foreign protection, inlet screens, filter debris, protects compressor blades, especially important for turboprops, turbo shafts, prevents engine damage, reduces maintenance costs. Yeah. That's it. This screen, it's an inlet screen mesh. It filters debris before it approaches the engine blades. And we are going to talk about the Belmov design used for ground testing, used for static operation, provides high efficient airflow, uniform flow distribution, minimizes pressure losses. So it has a large radius used for ground testing. Belmov. It's found in the wind tunnel. Now inlet systems for the turbofan and the turboprop. Turbofan inlets, they have a large diameter inlet. So here is showing the airflow. Some passes in the core stream, then the others is bypass stream. Larger diameter inlet design, sound reducing materials integrated, high mass flow rate capability, bypass stream and core stream management, noise reduction features, typical for commercial aircrafts. Then the turboprop, stock turbo shafts, they have a gearbox routing. So we are going to talk about air routing around the gearbox. They have a chamber for uniform flow distribution, airflow management, prevent shocking, impact design for smaller aircraft, accelerator mounting considerations typical for regional jets and utility aircrafts. Key differences: turbofans have a larger diameter, high bypass ratio, and for commercial focus. Then turboprop are compact, they have a gearbox integration, utility focus. Both have a uniform airflow distribution and have a pressure recovery optimization. Now compressors, types and their primary function. What's the primary function of the compressor? It supplies high pressure air to the combustion chamber in sufficient quantity to meet combustion burner requirements. But it must increase pressure of air mass from the inlet duct and discharge at high pressure. We have two types of compressors. We have a centrifugal flow compressor and the axial flow compressor. So we are going to compare them as you see in the diagrams below. Centrifugal is simple and rugged design. It has a high pressure raised per stage, airflow turned at 90 degrees, used in small commercial engines and APUs. Then axial flow, we know that here air passes parallel to the axis of flow. It has a high efficiency design, high mass flow rate capability, airflow parallel to the engine axis, and used in most modern jet engines. Now here we have an axial flow compressor operation and the stages. So it has a rotor blade, starter vanes, and the diffuser. The rotor blade accelerates the air and increases velocity and pressure. It has a multiple rotating blade stages action. It impacts energy airflow through rotation. As you see here, there is high pressure, high velocity. Then the starter vanes act as a diffuser, thus converting velocity energy to pressure energy. Designed, they have a fixed blade passages between the rotor stages. Direct airflow to the next rotor stage at correct angle. Then the diffuser function converts high velocity, high pressure air to high pressure, low velocity air. So the diffuser is to reduce the speed of the incoming air and it increases its pressure, as you see here at the back of this diagram. Location after the compressor stage. Purpose to prepare air for combustion chamber. Now here we have what we call the most common terms. We have compressor stall and surge. How we prevent and we manage this. Compressor stall, it is an aerodynamic phenomenon where blade angle of attack becomes too high. Airflow separation from the blade surface. There is localized airflow blockage, reduced compression efficiency, and can propagate through stages. As you can see, yeah, if the angle of attack is too high, it is stalled in the engine. Yeah. Then we talk about the compressor side. There's complete breakdown of the airflow through the compressor. Violent backflow of air goes back. Violent backflow of air, severe non-recoverable condition, can damage the engine components and requires engine shutdown. That's the surge cycle. See, pressure increases, then it goes on decreasing. Yeah. So how do we prevent and control? We have a variable inlet guide vane. So by adjusting the angle of the air entering the compressor, there is optimization of the blade incidence angle and prevent high angle of attack condition. That is it. Then you have the bleed valves. Releases excess pressure during low speed operation, reduce compressor loading, and maintain stable operating envelope of the air. So the bleed valve will reduce excess air in the compressor. That is it. Now here we have this graph of pressure ratio and mass flow. We can see a safe operating region, stable operation, where stall occurs and surge occurs. The surge region, we have the engine control system. How does this one work? Monitor pressure ratios, adjust fuel flow automatically, flowing, then prevent operating in the stall region. As you can see here, the engine control system detects pressure, RPM, and temperature. Then it can monitor the fuel, and it can also help in the opening of the bleed actuators and the variable inlet guide vanes. Thank you very much. As we shall proceed, we are going to proceed with the next module. All right, have a blessed day.